Hello students, in this video we will show how to use the derivatives to approximate nonlinear functions by linear functions. So consider f of x equal to x squared. And if we look at the picture of this graph, then at x equals to 1, here we can draw a line, a tangent line, and if we step away a little bit to the left or to the right of 1, then we can clearly see that the value on the tangent line is very close to the value on the curve. It doesn't matter whether we step to the left or to the right and move up, we can clearly see that this point in red is very close to this point in red. But if we are far away from this point x equals to 1, then we might be in trouble. For example, if we extend the line a little bit down and try to check it over here, we can clearly see that this blue point is far away from this blue point. So that means we have to stay close to 1. We have to stay very close to 1 for this approximation to work. So that's our main idea, that we will approximate f of x near x sub 0 by the tangent line. All right, so we need f of x to be differentiable function. So let f of x be differentiable at x equal to x sub 0. Then the local approximation, let's say linear approximation, because we're going to use linear function, linear approximation of f of x near x sub 0 is given by f of x approximately equal to, and here we have to put the tangent line. So let's try to find the tangent line for this function. So first of all, the slope would be equal to the f prime evaluated at x sub 0, and the point would be x sub 0, f of x sub 0, if we use function f of x and plug in x sub 0 into it. So y minus, so equation of the tangent line is y minus y1 equals m minus x1. So this is our y1, and our m is f prime of x sub 0. So that means we're going to get y minus f of x sub 0 equals m, which is f prime at x sub 0, times x minus x 0, since that's what our x1 is. So the only thing left is add f of x sub 0 to both sides. So if we add f of x sub 0 to both sides, our tangent line is y equals f of x sub 0. Let me write it a little bit lower. Y equals f of x sub 0 plus f prime times minus x sub 0. So that's what we're going to put over here instead of the tangent line. So equals f of x sub 0 plus f prime at x sub 0 times x minus x. Away from this is that approximately equal to f of x sub 0 plus f prime at x sub 0, x minus x sub 0 for x close to x sub 0. So that's the whole idea, and let's try to do this out in the exercise. So exercise, in this exercise, we have to, part E, find the local approximation of f of x equal to square root of x at x sub 0 equal to 1. And part 2 of the exercise wants us to use the local approximation, obtained in part 1 to approximate f of 1.1. I said it f at 1.1, but actually we can actually this out of 1.1. And to one calculated on the calculator. In this assignment, first one, the local approximation. F of x by f minus x sub 0 is square root of x. Start first thing 0, which is then we'll for this function f which is 1 to evaluate it at our answer will be square f of x minus and so basically what we have x function, which as we know, if we think about one, we have a tangent line approximation, and we would like to evaluate it at 1.1 and see how much the point on the tangent line would be different from the point on the curve itself. All right, so again, this line is 1 plus 1/2 x minus 1, and this curve is square root of x. So what would be f of 1.1, which is square root of 1.1? It would be approximately equal to 1 plus 1/2, then we have 1.1 minus 1. All right, so let's try to evaluate this expression. We have 1 plus 0.5 times 0.1. And it's easy to multiply 0.5 by 0.1. It's just going to be 0.05. And so we're going to get 1.05. 1.05. So that means that square root of 1.1 is approximately 1.5. So now we're going to accomplish part 2 of this. So we're going to take a square root of 1.1 and use a calculator to calculate it and compare it to this answer from part 1. So let's try to do that. We would like to do 1.1 and would like to take square root of 1.1. So that's our answer, which we're gonna see. It's really close. All right, so that was a good approximation. All right, just for the end this lecture right now because it's we're trying to keep the lecture small, and in this next lecture we'll do another example of linear approximation. All right, so see you in the next lecture.